All right, so we're going to start today's class with a little bit of review. We're going to do the product rule and we're going to do the quotient rule. Now, the two examples that I gave you are very straightforward. No fractions, no decimals, no special cases. This is just really to make sure that we remember the rule. Remember, you have your one sheet of notes. Hopefully you took it out, and then you're able to say, all right, product rule, first one. So for the product rule, we first have to know what the rule is. So the rule is derivative of the first times the original second plus original first times the derivative of the second. So if I work that out nice and slowly and carefully, when I take the derivative of the first one would be 3 times the original second one, x squared minus 3x plus 5, plus original first one, 3x minus 4 times the derivative of the second one, which is 8x minus 3. Stop there. If you got that correct, you got product, okay? But if you struggled with the next part, algebra, 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 right? Derivative of the first times the original second plus the original first times the derivative of the second. And then now it's all algebra. So we distribute the 3, we get 12x squared minus 9x plus 15. And then here we're going to have to kind of FOIL. So that would be plus 24x squared minus 9x minus 32x plus 12. Then simplify, combining like terms, 12x squared plus 24x squared, that's 36x squared. Negative 9x minus 9x is negative 18x. Negative 18 minus 32 gives us what? Negative 50x. And then 15 plus 12 is 27. Okay? So again, number one, do you know the product rule? And number two, can you simplify? Can you simplify? So the next one, we have two things being divided. So we're going to use quotient rule. So remember, quotient rule is derivative of the top times the original bottom, minus the original top times the derivative of the bottom, all over the bottom, original bottom, squared. Okay? So when we do that, the derivative of the top would be 8x minus 3 times the original bottom, 3x minus 4, minus the original top, 4x squared minus 3x plus 5 times the derivative of the bottom, which is 3, all over the original bottom, 3x minus 4 squared. So pause there. Make sure you got the derivative correctly. Get it correctly. And then the next part is simplifying. Now, again, this is where the mistakes generally happen. If you understand the rules, it's being careful. So on the first part, again, it's very similar to what we did earlier. 8x times 3x is 24x squared minus 32x minus 9x plus 12. Now, here's where I'm a little concerned. The subtraction has to get distributed and the 3 has to get distributed. So I could save a little bit of time. Instead of doing it twice, just move that 3 in front and distribute a negative 3. That would save us a little bit of time. So that's minus 12x squared plus 9x minus 15 all over 3x minus 4 squared. Then we're not done yet. We're going to simplify as much as we can. The denominator we're going to leave alone, 3x minus 4 squared. On the top, we have 24x squared minus 12x squared. That's 12x squared. Then we have negative 32x -9 plus 9. Put all those together, we get negative 32x. And then 12 minus 15, we get negative 3. And that would be your final simplified answer. So where we left off last class is I basically introduced chain rule, just real quickly at the end. So the idea is that if it's an E, ln, log, base raised to a variable, those are special cases. If two things are being multiplied, we got product rule. Two things are being divided, we got quotient rule. But what if I have, and again, for lack of a better term, stuff raised to a number? That's chain rule. And the general formula for chain rule is the exponent goes to the front, inside stays the same, subtract 1. But you have this feeling that you're not done. And you're not done because we took care of the exponent, but we didn't take care of the inside. So the last step would be derivative of the inside. Then, like we say, be careful, be careful, be careful. Simplifying, 3 times 2x is 6x, and I'd leave it just like that. So let me give you one more little straightforward. The only thing I'm going to do is I'm going to put a number in front. So pick a number. 8. So we'll have 8x. I'm going to put a fraction in there. Oh no, 2/3 minus 4x squared raised to the, give me another number. 4. Okay. So the only thing I've done differently, is I put a number in front. So just like we've done before, what happens to the number in front? It just stays in front. And I already know what's going to happen. 4 times 8 gives you 32. Okay. Inside stays the same. X to the 2/3 minus 4x squared. And then the 4 is going to become what? 3. And I'm going to pause there. And I'm going to let you finish this off. The last step is to take the derivative of the inside. That goes in the parenthesis at the end, and then simplify. I'll leave that part to you. So a little reminder, the 4 times 8 gave us the 32. Inside stays the same. 4 minus 1 is 3. And then the last step is derivative of the inside. So derivative of x to the 2/3 is 2/3 x to the negative 1/3. Don't be afraid of fractions. Then the derivative of negative 4x squared is negative 8x. Okay, we pause there. You have done chain rule. Fantastic. Okay, now, can I distribute the 32 to the first one? X to the 2/3 minus 4x squared. No, because of the raised to the 3. Exponents come before multiplication. But can I distribute the 32 to the other side? Yes, I can do that if you think it would make it a little bit easier. And details. So I'm going to keep it in parentheses. 32 times 2 is 64. Divided by 3. X to the negative 1/3. Minus 32 times 8. What's that? 256. Thank you. X times x to the 2/3 minus 4x squared raised to the 3rd. Now, at this point, you're going to ask yourself, okay, what can I do more? How can I keep going? And the answer is, I probably wouldn't. The only thing I would do, the only thing I personally would do, you don't have to, but I would make that x to the negative 1/3 positive by bringing it down. And I'm actually foreshadowing the future. So if you have a negative exponent, how do you make it positive? Move it down, vice versa. Minus 256x, and then x to the 2/3 minus 4x squared to the 3rd. Now, if you had an idea like, ooh, I can FOIL this, you can't, because this is raised to the 3rd. You'd have to write this one 3 times, simplify it, then multiply by that. It's not going to be, it's actually going to be uglier and longer and not anything to really work with. That would be your final answer. That would be your final answer. Okay, so here's the deal. I cover the first one. You're like, oh, this is pretty straightforward. 3 goes to the front, inside stays the same, subtract 1, times the derivative of the inside. That cleans up nicely. Ooh, this one had a fraction, but it's the same process. But still, you need to practice and you need to be exposed to more. But I've taught the lesson. That's chain rule, nothing new. Then he gives me this problem. I'd like you to find the derivative of square root 4 minus x squared. Find the derivative of square root of 4 minus x squared. So just like with derivatives, we're going to rewrite first. So again, not a derivative, not a derivative. How can I rewrite square root? Raised to the half. So x minus 4 squared raised to the half. We've done that many times before when we did derivatives. This is just another time. And now it's not product rule. It's not quotient rule. It's not a special case. It's chain rule because we have stuff raised to a number. So when I take the derivative, and please notice my notation, original, no prime. Derivative with that little apostrophe, prime. So it's going to be 1/2 4 minus x squared raised to the negative 1/2. Derivative of 4 is 0. Be careful. Derivative of negative x squared is negative 2x. So I'll pause there, see if we're okay. Now the simplifying. So what are some things we can do? Well, 1/2 times negative 2x would be negative x. And then see how this is raised to the negative 1/2? I would move it to the bottom and raise it to the positive half. And that would be my final answer. Now, if you didn't move it down and left it at negative 1/2, it's still correct. It is still the same answer. Just be careful. And again, I like making it positive because they're easier to do. The whole point is simplify it so when I plug in a number later, it's the easiest to plug in compared to the earlier ones. Okay, so again, now we're just going to practice and give you a little bit more experience. So here's another one. And again, there's a ton in between that you can practice and all that. I'm just picking certain ones. Okay, so let's do this one next. So let's say we had 1 over x squared plus x plus 4 raised to the third. Now, as you're writing this one down, your first gut instinct is quotient rule. But do you know how ugly and long quotient rule is? I would prefer not to do quotient rule if I didn't have to. This one, you could do quotient rule, and you're going to be here for a very long time doing quotient. Well, actually, not too long, but you could do quotient rule, but it will take a while. Versus try to rewrite it and do chain rule. Yes, you could do quotient rule. It's going to be kind of long, tedious. You'll be doing probably chain rule within quotient rule. It's going to be really long, or rewrite it. It's positive 3 in the denominator. If I move it up to the numerator, it's a negative 3. And then it's chain rule. In chain rule, I think we like a little bit better than quotient rule. The negative 3 goes in front. Inside stays the same. Negative 3 minus 1 is negative 4. Times the derivative of the inside, 2x plus 1. Notice that I'm just doing the derivative now. I'm not doing each one. We should be pretty good at derivatives now. So that would be the derivative. And then if I were going to simplify this one, the negative 4 would go to the bottom. X squared plus x minus 4 raised to the 4. You could distribute the negative 3, and you'd have negative 6x minus 3. It's one way you could simplify it for that final answer. So what we did was we learned all the special cases up front. The way the textbook likes to do it is they like to put the special cases throughout because the reason why the number in front stays in front is because of product rule. The reason why E and ln and log, there's a little bit of chain rule in there, right? So this is the point where they start giving more examples because this is the why the special cases work, at least the little more difficult ones. So I'm going to give you 3 examples to try. And you're going to think it as chain rule, special case, which is totally fine. And just think of it as overall practice. So the first one's going to be 3x squared plus 1 raised to the 3 over 2. Take the derivative of that. The second one is going to be the derivative of e to the 2x to the third plus 5. And then the last one would be take the derivative of ln of x squared minus 4x plus 2. Okay, so this is a good chance to use your 1 page of notes with all the special cases and all that stuff and work on all three. So as we work through all three of these, a couple things to remind you. They're not going to be labeled product rule, quotient rule, chain rule, special case. You're going to have to be able to look at it and identify what it is. So the first one is not two things being multiplied. It's not two things being divided. It's stuff raised to a number. So we then know this is going to be chain rule. So the 3/2 goes to the front. Inside stays the same. 3 over 2 minus 1 gives us 1/2. Okay, derivative of the inside would be 6x, and you have done chain rule. So you got that part done. We're going to simplify it in a minute, but let's make sure we're comfortable with that. Then, if we were going to simplify, 3 over 2 times 6 is 18 over 2, which ends up being 9x, 3x squared plus 1 raised to the 1/2. Okay, if somebody else had happened to write 9x square root of 3x plus 1, would that also be correct? Yes. Again, keep in mind, there's a lot of ways to write it. My job is to figure out which is correct, which is not. Your job is to just simplify. Make sure you simplify. Make sure you simplify. Now, for the next two, these are both special cases. Remember, you don't have to memorize. You can use your 1 page of notes. So when you're working on this, let's see if those notes make sense. And if not, add to them. You may need the words because it's been a little while since we've done special cases. Look at your notes, make sure it makes sense to you. But how do you take the derivative of a special case? Step 1, rewrite it. Step 2, derivative of the exponent, 6x squared. So if I was going to rewrite this, the way it is okay. But I would probably put 6x squared e to the 2x to the third plus 5. Okay, put a little dot in between if that helps you as well. Okay, questions on the second? Nice catch. Don't forget the squared here. Okay. Okay, now we have ln. Again, can you read your own notes? Do you remember how to do it? This one, if we're taking the derivative, it's 1 over the original, x squared minus 4x plus 2, whatever we're taking the ln of, times the derivative of the inside, which would be 2x minus 4. Another way people like to write this is the derivative of whatever you're taking the ln on top and the original, whatever you're taking the ln on the bottom. There's no base to deal with. That would be your final answer. Now, again, if you could simplify it, we would look at it, but I think that's it. So we've learned special cases, product rule, quotient rule, chain rule, but remember, they can also be mixed. So I'm going to make up one here. I'm going to say, take the derivative of, let's say, 3x squared minus log 7 x squared minus 1 raised to the 7. Okay, give that one a try. So we know product rule, quotient rule, chain rule, special cases. We have to learn all of them. And we also have to know how to be able to do all of them, possibly at the same time. So here's the idea. Overall, if you had to pick special case, product rule, quotient rule, chain rule, overall, what is this problem? Chain rule. Okay, so overall, this is chain rule. So I'm going to do chain rule. And before I do it, let me just explain to you what I'm going to do. Exponent's going to go to the front. Inside stays the same. Subtract 1. And then the last step is derivative of the inside. Is everybody clear? That's all I'm going to do. So you see this as a brand new problem. And for me, it's just chain rule. So 7 times 4 is 28. Inside stays the same. 7 becomes 6. And then what's the next step in chain rule? Derivative of the inside. So now I'm going to do the derivative of the inside. The derivative of 3x squared is 6x minus the derivative of a log. It's just the derivative of the inside. And what happens to be inside is a log. Do we know how to take a derivative of a log? Yeah, it's 1 over, in parentheses, whatever you're taking the log of, ln of the base times the derivative of the inside, which would be 2x. Now, I agree with you completely that that looks very ugly, right? Or some would say very beautiful. But it's still chain rule. Exponent goes to the front. Inside stays the same. Subtract 1, and then derivative of the inside. But when I had to take the derivative of the inside, there was a log in there. But I know how to take the derivative of a log. Now, the part you're a little worried about is how to clean it up. I'm actually not going to clean it up that much. I'm going to leave the 28 there. I'm going to leave the original there. Here, I'm going to put 6x minus 1 times 2x is 2x over x squared minus 1 ln of 7. And I'll probably just leave it like that. Could I distribute the 28? I could. Or I could just multiply by 28 at the end. Both are okay. Probably a little more simplified if I distributed the 28. I can't distribute the 28 to the first one, but I could to the second. But I'm going to leave it just like that. Because again, if I had to plug into it, at the end, you multiply by 28. I don't think that's too much work. But if I wanted to distribute it in, I totally can. Okay? But take a moment to look at it. You can do one within another one. But overall, this was chain rule. Overall, this was chain rule. That concludes chain rule. And the next section is related rates. But please know, in your notes, one of the reasons why I'm using the notes is there's a bunch of other examples you can do. And the answers to all the matched problems are on the bottom of the notes. So if you just want some extra practice right away, they're in the notes. They're in the notes, and you have the solutions. And you have the solutions. So first of all, related rates. I'm going to tell you that sometimes people are a little confused by related rates, okay? There's a lot going on, and my advice is let's do one and then practice it. So it's going to seem a little weird in the beginning because a lot of things are going on, but the idea that it's related rates, it's the study of related rates provided a method for determining the precise relationship between the rate of increase or decrease of two quantities. So the term rate, like for example, miles per hour, feet per second, it's going to be involved. There's going to be rates involved, how things are changing. And it's a little weird. Just kind of bear with me. Okay. So here's the one I'm going to introduce. A 26-foot ladder is leaned against a wall. The ladder slips and the top of the ladder begins to slide down the wall. As that happens, the bottom of the ladder slides along the floor away from the wall. As the ladder falls, the distance from the floor to the top of the ladder and the distance from the wall to the bottom of the ladder are both changing. If the top of the ladder slides down at 2 feet per second, what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet away from the wall? And you're like, let's just go home now. Okay? No, it's not that bad. But let me explain to you what's happening and set it all up, and then you'll see it's not that bad. Okay? First of all, can we all agree that we have a 26-foot ladder? Good so far. The distance from the wall to where the ladder begins, we're going to call X. That's a distance. Are we good with that? And the distance from the bottom of the floor to the top of the ladder is y. It's not 26 because the ladder is leaning, right? So we have distance, distance, distance. They're all in feet. Good so far? Some of you may be thinking ahead. Hey, isn't this a right triangle? And do we know anything about right triangles? What do we know? 90 degrees. Pythagorean theorem, right? Pythagorean theorem says a squared plus b squared equals c squared. If it's a right angle, it follows a squared plus b squared equals c squared. Perfect. You're now going to use it. So x, and again, remember c is the hypotenuse. So a leg squared plus a leg squared equals the hypotenuse squared. So in this case, we have x squared plus y squared equals 26 squared. And I'll tell you what that is right now. 26 squared is 676. Stop there, and you've now begun your related rates problem. Okay? So it's going to start with that formula, but I kind of jumped the gun a little bit. Why did I jump the gun a little bit? What I mean by that is I need to first write down what I know, what's given. And they did give me some information, right? They told me that the ladder is 26 feet. So we got that. Okay? And they told me that the distance x is 10 feet. In the problem, they told me that the distance from the wall to the ladder is 10 feet. So the ladder is given. X is given. Unfortunately, they did not give me y. They did not give me y. They did give me something else. What they gave me was 2 feet. The ladder slides down the wall at 2 feet per second. So it's telling me how y is changing. dy over dt. Let me explain that. dy is the derivative of y. How y is changing over, all of this is over t for time, Now, this is a little tricky. I would help you out with this, but since the ladder's falling downward, we call it -2 feet per second. -2 feet per second. -2 feet per second. This is where we're introducing a rate. Okay? But they didn't tell me dx over dt. That's not given. So if we pause there, look at what is given, and look at our starting equation and how we got it, let's just pause there and make sure we're comfortable. Now, here's where things get a little weird, and we're going to go through it super slowly. I have a formula that uses x and y. That can totally help me to find x and y. Are we okay? But this formula is not going to help me with dx over dt and dy over dt. X and y are the distances. I want the rates. So what I'm going to do slowly is take the derivative of this equation. Nice and slow. There's going to be one part that's a little weird, and we'll talk about it. We're going to take the derivative of this first equation. What's the derivative of x squared? 2x. Perfect. But this is where it gets a little weird. But what we're doing is dx over dt. So we have to include dx over dt because that's the rate. That's the rate. So after you take the derivative, you include dx over dt because it's the derivative of x with respect to time. There's now a time aspect going on. Okay? Then plus, what's the derivative of y squared? 2y, but I'm going to have to put in dy over dt. Okay, I know it's a little weird, but we're taking the derivative of x with respect to time. It's a rate now. The derivative of distance is a rate. Equals, what's the derivative of 676? 0. And I don't put anything after it because anything times 0 is 0. It won't change. So here's the deal. If you can get to this point, the rest is like a little game. You now have one equation and two equations. You're going to use those two equations to find the two unknowns. So the two unknowns are y and dx over dt. Now, if you wanted to try to get dx over dt, I would use the second formula. Do you know what x is? Yep, it's 10. Do you know what y is? No. So should I find this one first? Nope, because I need y. So let's find y first. Do you think I'll use the first equation or the second equation? The first equation. X squared plus y squared equals 676. So our first step, we'll label it step 1, find y. So step 1 is to find y. Step 1 is to find y. So I want you to plug in for x and solve for y. Plug in for x and solve for y. So we know that x is 10. That's part of the given. We don't know y. So we're going to do some algebra to solve. 10 squared is 100. 100 plus y squared equals 676. Subtract 100. Subtract 100. Y squared equals 576. Do I want y squared or y? So what do? Square root, square root. Now, please keep in mind, you actually do get two answers, a negative and a positive. But we're talking about a distance. So can distance ever be negative? Nope. So we're going to stick with a positive one. And the square root of 576 is 24. So you just found out that y is 24. So now we know that y is 24 feet. Good so far? So we did step 1. We found y. What do you think step 2 is going to be? Now step 2, we're going to find what? Good. Dx over dt. Now to find dx over dt, we're going to use which formula? The second one. And if some of you are wondering, could I do that first? You couldn't. We didn't have enough plugged in. I couldn't do the first one. So I'm going to pause and I'm going to put the equation here. And I'm going to say, plug in everything you have and solve for what you don't. So now we go to the second equation, and I'm going to plug in all the ones I know. So I know x is 10. I don't know dx over dt. I know that y is 24. I know that dy over dt is -2, and the negative does matter. Very important. Equals 0. And then when I go to simplify all this, this is going to be 2 times 10, that's 20 dx over dt, minus 96 or plus -96 equals 0. Add 96, add 96, 20 dx over dt equals 96, divide by 20, divide by 20, dx over dt equals 4.8 what? Feet per second. Okay, so we now found that the rate is 4.8 feet per second. 4.8 feet per second. Okay, so let's back up and talk about what we found. Okay, so if we go back to the original picture, what's the distance for x? 10 feet. What's the distance for y? 24 feet. Perfect. Now, what is happening is the ladder slipped. The ladder slipped. So how fast is the ladder going downward? How fast is the ladder going downward? 2 feet per second. And because it's downward, we call it negative. Are we okay? How fast, because again, two things are happening. It's falling like this, and they're not falling at the same rate. How fast is the ladder falling on the bottom? 4.8 feet per second, and it's positive because it's going outward. It's going out. That's what we just solved. That is related rates.